Hello, this is Precalculus, Chapter 2, Section 1, Linear and Quadratic Functions and Modeling. By the end of this lesson, you'll be able to recognize and graph linear and quadratic functions and use those functions to model situations and solve problems. So it's the first section out of a new chapter. There's a lot of basic information that'll be displayed. A lot of the material should seem familiar to you from both Geometry and Algebra 2 classes. What I'll start with before I get into linear and quadratic functions is just talking about polynomial functions in general. Uh, you've heard of polynomial functions before. We've talked about them. This might be a new notation for you. Basically, when you're talking about a polynomial function, consider the that all this means is you could have a number of different terms. N in this situation represents the highest degree that the x variable is raised to. So you could have n plus 1 number of terms, or you could just have one term, no matter what that degree is. It all depends on what the coefficient is on each term. Obviously, whenever a coefficient is 0, that term doesn't really exist. So basically, the degree of the polynomial is the highest degree that of the variable is raised to. Sometimes the polynomial terms are out of order, so make sure that you look for the highest degree and don't just look at the first term. If it's written in the proper form, the terms will be in descending order according to the exponent. Whichever term has the highest exponent will have a coefficient. We call that coefficient the leading coefficient. Of course, if no number is out here, then the leading coefficient is 1. It's not 0. And if there is a term that has no variable, well, it actually did. It's just that the variable was raised to the 0 power, which is the same as multiplying by 1. So whenever you just have a number with no variable attached, we call that the constant. That's the constant. Just some technical information. The 0 function is f of x equals 0. It is a polynomial function. We don't really use it that often, but just to make note, it has no degree and no leading coefficient. I also mentioned that here, the 0 function. The degree is undefined. This is just a list of polynomial functions of no or low degree. We have the constant function, where f of x would just equal a number that's not 0. And that's a 0 degree polynomial. We have a linear function that you're very familiar with, f of x equals ax plus b, where a doesn't equal 0, of course, because if it did, we'd just have the constant function. That's a first degree polynomial. And then the quadratic function, f of x equals ax squared plus bx plus c. And again, a can't equal 0, otherwise we would just have the linear function. The quadratic function is a degree 2 polynomial. It should all be familiar to you. Linear function you know as y equals mx plus b. You can use point slope form or slope intercept when working with that. I know I'm going kind of fast, but I know you don't want these videos to be too long, so I'll try to hurry. What I would do is I would pause your video here after and read this question and see if you could interpret it and understand what it's asking. After you do that, I'll give you this information. Write an equation for the linear function f such that f of negative 1 equals 2 and f of 2 equals 3. You've been asked this for years. It's just asked in a different way. This is simply saying, write the equation of a line that goes through the point negative 1, 2, and 2, 3. Or goes through those points. That's a 2 and that's a 3. Sometimes my computer pen gets a little crazy. So how would you answer this? You'd find the slope using those 2 points and then plug them into either point slope or slope intercept. And we want to get them back into the form shown above, which was slope intercept form. So if you found this, you can pause and do that yourself. So if you didn't pause, I'm going to give the answers. Here we go. Here's a slope of 1/3. I plugged it into point slope first. Remember, this is point slope right here, where you could plug in either of the points given for x1, y1, and then the slope goes in for m, as I did here. And then once you get the y all by itself and distribute the 1/3, you get this answer. So there's your new function, or there's the function that represents a line that contains those points. All right, moving on. Average rate of change. That's just a fancy way of saying slope. Um, so you can pause that and take a look. Constant rate of change theorem. Again, this should seem like obvious information to you after you read through it and understand what it's saying, but I'll read it for you. A function defined on all real numbers is a linear function if and only if it has a constant non-zero average rate of change between any 2 points on the graph. What that's saying is a function is a linear function if you take any 2 points on that function and you find that they have the same slope. Any 2 points, no matter what, you get the same slope. Or if you take any 2 points on a function and you get the same slope no matter what, then it is a linear function. So you know that, you've known it for years. The next piece of information is it's just a chart kind of summarizing most of what you know about linear functions. It's a great way to review and study, is to be able to try to write down everything you know. So what I wrote was a linear function is a polynomial of degree 1. Algebraically, it's f of x equals mx plus b, where m can't equal 0. Graphically, it's a slant line with a slope of m and y-intercept b. Analytically, it's a function with a constant non-zero rate of change, m, that's your slope. When m is greater than 0, the function's increasing. When m is less than 0, it's decreasing. And its initial value, f of 0, is b. So one thing to really make note of, you'll see the phrase initial value often. That's basically saying plug 0 in for x, and what's the y value you get. Or it's the same as saying the y-intercept. So don't be confused by the phrase initial value. You've used that for years also as y-intercept. What I'd like to talk about now is the correlation coefficient. The correlation coefficient R, you use it with a linear equation or linear function. And basically, we can use that correlation coefficient to tell us a couple of things. We can use it to determine how closely the data correlates to the equation we're using, and whether it's a positive correlation or a negative correlation. So I'll just talk about that correlation coefficient first, and then I'll show you where you get it from. So it's always going to be between -1 and 1. If it's greater than 0, there's a positive relationship or correlation. If it's less than 0, there's negative. And then if you take the absolute value of the correlation coefficient, if it's closer to 1, then the data has a strong linear correlation, which means it fits your data more closely than if it was farther away from 1. Or if it's closer to 0, then it's a weak correlation, or the data is more spread out. Here's a nice diagram to show you examples of that. Here'd be a strong linear correlation. It kind of follows a line. This is a little bit weaker, and then this is hardly any or no linear correlation. All three of these are positive. I'm talking about the top ones. All three of these have a positive correlation of different levels. And then these are negative correlations, where this one's stronger and this one's a little bit weaker correlation. Graphically, this is where you'd go to Stat, Edit, type in some information. If you want to pause this, type it in to see if you do the same thing as me. You certainly can. Type it in. Remember, if you're gonna look at your graph, you go to Stat Plot. Make sure you turn it on. Make sure you don't have an equation in your y equals. Then I just go right to Zoom Statistic, which is number 9 if you scroll down. And then it shows a nice little graph. From there, I want my regression equation. So what I have to do is I have to go back to Stat, over to Calculate, and I want my linear regression equation, number 4. Press Enter, and that R on the bottom there, that's my linear regression coefficient, or my regression coefficient that we've been talking about here, my correlation coefficient. So that's really close to 1, so we know that it's a positive relationship and that it's pretty strong. Up here you can see the equation of the line that it's talking about would be y equals 2.607x plus 2.464. So if you were asked to superimpose that on your graph, what you'd be asked to do is basically, and you can watch this to see a shortcut on how to do that, but you can always just write it down, copy it and type it in. But I like to use my calculator to more of its abilities than that. So you can kind of look at what I'm doing and copy it in there. When you go to graph, it'll superimpose it onto the graph, and you can see the relationship. So that looks really nice. You can see how it has a strong relationship. What I wanted to show you also was this r squared value. If I bring back that information, there's an r squared value. What you're going to do with that is you're going to compare different regression equations and see which ones fit the data that you have more closely. So if you go back to statistics, you can see in statistics and calc, there's a linear regression, number 4, a quadratic regression, a cubic regression, a quartic regression, and so on. There's a bunch of different ones we'll use throughout this year, and you'll use the r squared to compare between the different ones. So to kind of summarize all that stuff, when you do a regression analysis, you enter and plot the data into a scatter plot. You find the regression model that fits the problem or situation. You superimpose the graph of the regression model onto the scatter plot and observe it, see how they compare. And then you would use the regression model to make predictions called for in the problem. That's the process. So switching gears a little bit, just like in last chapter we talked about different kind of transformations of basic functions. Well, you'll do the same thing here. So if you wanted to, you can pause after you look at this problem and see how you would describe how to transform from x squared to f of x equals 2 times x minus 2 squared plus 3. I'll reveal the answer, and you can take a look at that and see if you answered it the same way, and then also think about where that graph would be, if you can imagine. So you should have saw a vertical stretch by 2 because of the 2 out front. Vertical stretch by a factor of 2. Shift 2 to the right because of that 2, and shift up 3 because of that. Some things to note about a quadratic equation. If that a value out front, so whatever the number is on the x squared, if it's positive, it's going to open up. If it's negative, it's going to open down. So real easy to remember. If it's positive, it's happy. So you got a little smiley face. If it's negative, it opens down, so it's got a big frown on its face. Yeah, it's not very happy. I just made that up, so that'll help you anyway. Okay, so the vertex form of a quadratic is the next thing you haven't used a lot, and that's this right here. You're going to be relating the vertex form just to the standard or general form. Notice the A, B, and C. Whatever the sign is out in front goes with the A, B, and C. Notice there's also an A here, an H, and a K. HK is the vertex. X equals H is the axis. That's like the axis of symmetry where the parabola would fold on top of itself. You need to make note of this formula. H equals negative b over 2a. And K, this formula, K equals C minus A times H squared. A lot of students remember Ka. I don't know why, they just like to make that noise. But you can use these two equations to find the vertex of the parabola if you are given the general or standard form. So you have to be able to find vertex form using these, and also using completing the square. So to use those, I'll just show you an example of that here. Again, try it yourself. Use those two formulas. See if you could do this problem by yourself to change this from this form to vertex form. So here's the result. Make note that, A was 2, B is -8, and C was 11. So I found H first was 2, then I found K, which I needed H, to help me with that. So that was 3. And then it's just plugging in numbers. Remember, you need the A out front. H goes in there. It's the standard, so if H is +2, then it's a -2 on the inside. And if K was a +3, then it's +3 on the outside. That's the K value. So then you also need to be able to use completing the square to convert to vertex form. So why don't you pause here, see if you can do that. On another video, I'll go through this process. I don't want to make this video too long, but I will reveal the answer. So pause, try it, and then take a look at the answer. So what you can see here is I had to factor out a -4 from the first two terms because the leading coefficient needs to be a 1. Then inside here, when you're completing the square, you always take half of the b value and square it. And remember that whatever you end up adding in here, you have to cancel out over here. So since it's being multiplied by a -4, you've got to cancel it out over here as well. Simplify. Remember, if you factor this out, it becomes this. And then when you combine your like terms in the end, you just have your final answer down here. And notice you have the vertex of 3/2, 1. And that's it. I've run out of time here on this video, so I'll let you just copy down this summary of the quadratic function. And so pause here, copy that down, read through, and then the same with the vertical free fall motion.